Welcome back, everyone. Today's topic is classical planning. And in classical planning, we owe a lot to our old friend Shaky, shown here at the Computer History Museum. So, what is planning? We can define planning as coming up with a plan of actions to achieve some goals. Planning is an essential part of AI. We have already studied search based planning agents. These agents work in deterministic, static, and fully observable environments. They use an atomic representation of states, and they need domain specific knowledge to make their search more efficient. Now, in classical planning, agents work in deterministic, static, and fully observable environments as well. However, they use a factored representation of states and they combine logic and search. AI researchers have been faced with a challenge in representing the effects of action. Let's take as an example my office here. To represent the current state, I can say that the window is open, the lights are off, and the door is closed. Now let me walk over and close the window. What are the effects of my action? Well, the window is now closed, the lights are still off, and the door is still closed. So the question is, do we need to specify the result of an action on all the state variables? Do I need to say that me closing the window had no effect on the door and it had no effect on the light? So that's the frame problem. The frame problem is this challenge of representing the effects of an action without having to represent explicitly a large number of intuitively obvious non-effects. So how do we capture what's relevant and what is not relevant here? There is this common sense law of inertia that tells us that an action can be assumed not to change a variable unless there is evidence to the contrary. STRIPS stands for Stanford Research Institute Problem Solver. It was initially an automated planner developed for Shaky at SRI in 1971. The same name was later used to refer to the language used for the inputs to this planner. This language is the base for most of the languages used in planning today. Now, in this class, we will not study strips, we will study Pddl, and Pddl stands for Planning Domain Definition Language. It was developed in 1998 and it's derived from the strips planning language. With Pddl, we can specify initial states and goal states. We can also specify action schemas in terms of preconditions and effects. Each state is represented as a conjunction of first-order logic literals, representing atomic facts. We call them fluents. So, for example, we can have the following state: add SAM SJSU and add plane 1 SFO and add plane 2 SJC. Now there are two restrictions. These literals must be ground. They cannot contain any variables. So I cannot write at XSFO to represent a state. That is not allowed. The other restriction is that these literals must not have any function. So at brother Anna SJSU is not allowed either in a state representation. The names are supposed to be unique. So when I have a state at plane 1 SFO and at plane 2 SJC, plane 1 and plane 2 are two distinct objects. We have this closed word assumption that tells us that whatever is not explicitly stated is assumed to be false. So with this assumption, there's really no need for negative literals in a state representation. If something is supposed to be false, we just omit it from the state representation. We only include positive literals in the state representation. So based on what we just said, which one of the following is the most concise and sufficient representation of the state where only one plane P1 is at SFO? P2 is also a plane, but it's not at SFO. I'll give you a minute to try to come up with the answer. So the answer is B. We know that plane P1 is a plane, P2 is a plane, P1 is at SFO, and SFO is in airport. We do not need to list the fact that P2 is not at SFO. We do not need any negative literals in the state representation. So to represent the initial state of a problem, we write init and we follow it with the conjunction of ground literals that describe the state. So how do we represent actions in Pddl? We use action schemas to represent actions. An action schema includes an action name followed by a list of variables. For example, fly P from 2. A precondition, and the precondition is a conjunction of positive function-free literals. These are the conditions that must be true for the action to proceed. And then we have an effect, and the effect is a conjunction of positive or negative function-free literals. So here's an example of an action schema. We write action, and then we follow it by the action name, followed by a list of variables. We have 3 variables here, P, from, and to. The precondition consists of a conjunction of positive function-free literals. And the effect of this action is that P will no longer be at from, not at P from, and P will be at 2, so at P2. So that's an action schema that describes the fly action. Note that we have positive literals in the precondition, but we may have negative literals in the effect. So it's important to note that each schema represents a whole set of actions. It's not just a single action. We can think of the variables P, from, and to as universally quantified. We can substitute values for these variables and get one ground action. For instance, we substitute P with plane 1, from with SFO, and to with JFK, and then we get the single action, ground action, fly plane 1 SFO JFK. And we have to apply the substitution to the precondition and to the effect as well. Any variable in the effect of an action schema must appear in the action's preconditions. So that's a requirement of the language. We cannot have variables that appear here and here in the effect without appearing in the precondition. Note that there is no explicit reference to time here. The precondition implicitly refers to time t and the effect to time t plus 1. All right, so based on what we have just learned about action schemas, is this a valid action schema? Take a minute and think about it. All right, so we do have an action name followed by three variables. The precondition consists of a single literal. It has no functions. And the effect has negative literal and a positive literal. But what's the problem here? The problem is that the effect includes the variable 2, and the variable 2 does not appear in the precondition. And that was one requirement, that any variable that appears in the effect must also appear in the precondition of the action schema. So in classical planning, we deal with problems where most actions leave most things unchanged. If I have hundreds of airplanes and I fly one airplane from JFK to SFO, the status of all the remaining airplanes is unchanged. So how do we address the frame problem here? Remember, the frame problem is that challenge of representing the effects of an action without having to explicitly represent non-effects. So in Pddl, we are actually addressing the frame problem by specifying the result of an action in terms of what changes. Anything that stays the same is not mentioned in the effect. So based on this, let's take a look at the drive action. The drive action schema is a schema where we are driving a specific car, car 1, from a location to another location, and X represents our driver. So which of these options is the correct way to formulate the effect of the drive action? Take a minute and think about it. So the important thing here is to remember that we only include what has changed in the effect. So after the drive action, X is at 2, location 2, and car 1 is at location 2, but we have to include the fact that X is no longer at location from. So option A is not correct because it's missing the fact that X is no longer at from. Now, let's take a look at option B. Option B tells us that X is no longer at from and car 1 is no longer at from, and X has a driver's license. So this part here has not changed. It should not be included. Plus, we are missing the fact that X should be at 2 and car 1 should be at 2. Let's take a look at this here. So here again, we are missing some negative literals, and we don't need to include the fact that X has a driver's license. This has not changed, so we do not include it. Option D seems to have everything we need. X is at 2, car 1 is at 2, X is no longer at from, and car 1 is no longer at from. And option E has this extra literal that we do not need to include because it has not changed. We do not include it in the effect. So how do we determine which actions are applicable from a given state? An action is applicable in a state S if A's preconditions are satisfied by state S. So when an action schema contains variables, that schema may have multiple applicable instantiations. Let's look at this example. We have the initial state, P1 is at SFO, P2 is at JFK, and P1 is a plane, and P2 is a plane, and SFO is an airport, and JFK is an airport. And we have the fly action schema. Now the fly action can be instantiated by unifying a state S with the preconditions. So here we're looking for a unifier, the substitutions of the variables p, from, and to that will make the precondition identical to clauses in the initial state. Here's the possible unifier. We substitute P with P1, from with SFO, and to with JFK. And when we apply that substitution to our action schema, we get the following ground action. But we could also use a different substitution. We could use the substitution where P is replaced by P2, from is substituted with JFK, and to is substituted with SFO. So we get a different ground action. We get the ground action fly P2 JFK SFO. So both ground actions here are applicable in the initial state. So assuming we have an action and we have a starting state, how do we apply the action? How do we figure out what the successor state is? So starting from a state S, to apply an action A, we remove the negative literals in the action's effect. Here there's only one negative literal, not at P1 SFO. We put these negative literals in a list. We call it the delete list, del of A. Then we add the positive literal in the action's effect. There's only one positive literal in the action's effect. It's at P1 JFK. We put that in a list. We call it the add list. And now we compute the successor state by removing the delete list from state S and adding the add list. So we end up with add P2 JFK and plain P1 and plain P2 and airport SFO and airport JFK and add P1 JFK. So we've seen how to represent initial states, we've seen how to represent actions, and we've seen how to compute the successor states. The last thing that we need to figure out is how do we represent a goal in Pddl? So a goal in Pddl is a conjunction of literals, positive or negative, and they may contain variables. Here's an example. Our goal may be to have some plane at SFO. We would write that as goal at x SFO and plane x. So here we have a variable. Now the variables are treated as existentially quantified. Our goal here is to have at least one plane at SFO. And the state is a goal state if it entails the goal. So the state S where plane 1 is at SFO and plane 1 is a plane and plane 2 is at JFK and plane 2 is a plane entails the goal. So it is a goal state. So in Pddl, a set of action schemas defines a planning domain. A planning domain may be applicable to more than one specific problem. Now, a specific problem within the domain is defined with the addition of an initial state and a goal. And the problem is solved when we find a sequence of actions from the initial state to a state that entails the goal. As a Pddl example, we'll look at an air cargo transportation planning problem. The problem involves loading and unloading cargo and flying it from place to place. The problem can be defined with three actions: load, unload, and fly. The actions affect two predicates. In CP means that cargo C is inside plane P, and at XA means that object X, either plane or cargo, is at airport A. When a plane flies from one airport to another, all the cargo inside the plane goes with it. We'll say that a piece of cargo ceases to be at anywhere when it's in a plane. The cargo becomes at the new airport when it's unloaded. So at really means available for use at the given location. So here are the action schemas. The load action, to load C on P at A. The preconditions are that C must be at A, P must be at A, C must be a cargo, P must be a plane, and A must be an airport. And the effect is that C is no longer at A and C is in P, inside the plane. The unload action has the following preconditions: in CP and at PA and cargo C and plane P and airport A. The effect now is that C is now at the airport and it's no longer in the plane. And the fly action has the following preconditions: at P from and plane P and airport from and airport to, and the effect is not at P from and at P to. So that's our planning domain for the cargo transport problem. Now, if we add an initial state and a goal to our planning domain, we get a specific problem that we can solve. So let's add this initial state. Let's say C1 is at SFO, C2 is at JFK, P1 is at SFO, and P2 is at JFK. C1 is cargo, and C2 is cargo. P1 is a plane, and P2 is a plane. JFK is an airport, and SFO is an airport. Now our goal is to have C1 at JFK and C2 at SFO. So the initial state, this goal, and the action schemas we've seen before together define our problem. So PDDL is obviously less expressive than first-order logic. There is no way to say move all cargo to SFO. We don't have any universal quantifier in the goal. Any variable in the goal is assumed to be existentially quantified. There's no way to concisely express global constraints either. So let's say we can have no more than 100 planes at a given airport. There is no way to describe that constraint in PDDL. And there is no explicit time representation. We may need the cargo to be at JFK by 5 p.m. There's no way to represent that in PDDL.